Let me double check that the stream is working as per usual. Alright, we're live. Let's check that we have sound. Okay. And looks like we're all good. No more dilly-dallying. Let's go. Chapter 20. Vector spaces. In a physical system, a quantity can often be described with a single number. For example, we need to know only a single number to describe the temperature, mass, or volume. However, for some quantities, such as location, we need several numbers. To give the location of a point in space, we need x, y, and z coordinates. Temperature distributions over a solid object require 4 numbers, 3 to identify each point within the object, and a 4th to describe the temperature at that point. Often, n tuples of numbers, or vectors, also have certain algebraic properties, such as addition or scalar multiplication. In this chapter, we will examine mathematical structures called vector spaces. As with groups and rings, it is possible to give a simple list of axioms that must be satisfied to make a set of vectors a structure worth studying. Section 20.1, Definitions and Examples. A vector space V over a field F, note here is going to be important, the fact that it's over, this is like a field, and it's F, is an abelian group with a scalar product A dot V. So we have a abelian group V plus equipped with an operation called dot that takes F and a vector in V and gives us another vector in V, such that we have associativity of the product here, alpha beta, alpha beta V. So we have associativity of scalar multiplication. We have that scalar multiplication is distributive. So alpha plus beta V is equal to alpha V plus beta V. We have scalar multiplication distributive over vector multiplication. So alpha V plus W is equal to alpha V plus alpha W. And we have that 1 times V is equal to V, where alpha and beta are in F, and U and V are in V. The elements of V are called vectors. The elements of F are called scalars. It is important to notice that in most cases, 2 vectors cannot be multiplied. In general, it is only possible to multiply a vector with a scalar. To differentiate between the scalar vector, the scalar 0, and the vector 0, we will write them as 0 and bold 0, respectively. Let us examine several concepts of vector spaces. Some of them will be quite familiar, others will seem less so. So, example 20.1. The n tuples of real numbers, denoted by r to the n, form a vector space over R. Given vectors u equals u1 all the way to un, and v is equal to v1 all the way to vn in r to the n, and alpha just a scalar in R, we can define vector addition by u plus v is equal to u1 all the way to un plus v1 all the way to vn is equal to u1 plus v1, u2 plus v2, and we add un vn. So we define vector addition coordinate-wise. And scalar multiplication can be defined by alpha u is equal to alpha u1 all the way to un is equal to alpha u1, alpha u2 all the way to alpha un. So we distribute the scalar over the interior coordinates. Example 20.2. If f is a field, then fx, or f adjoint x, the set of polynomials with coefficients in f, is a vector space over f. The vectors in fx are simply polynomials, and vector addition is just polynomial addition. If alpha is in f, and p of x is in f of x, then scalar multiplication is defined by ap of x, where we distribute, once again you can think of it coordinate-wise, over the vectors, or over the polynomials. Example 20.3. The set of all continuous real-valued functions on a closed interval, ab, is a vector space over R. If f of x and g of x are continuous on ab, then f plus g of x is defined to be f of x plus g of x. Scalar multiplication is defined by alpha f x is equal to alpha f of x, for alpha in R. For example, if f of x is equal to sine of x and g of x is equal to x squared, then 2f plus 5gx is equal to 2 sine of x plus 5x squared. Example 20.4. Let V be equal to the Q adjoint square root of 2, which is a set of all A plus B square root of 2 with A and B in the rationals. Then V is a vector space over Q. If u is equal to a plus b squared root 2 and v is equal to c plus d squared root 2, then u plus v is equal to a plus c plus b plus d square root of 2 is again in v. Also, for alpha in Q, alpha v is in V. We will leave it as an exercise to verify that all the vector space axioms hold for V. Proposition 20.5. Let V be a vector space over F. Then each of the following statements is true. 1. 0.v, or 0 times V, is equal to the 0 vector for all V in V. 2. Alpha times the 0 vector is equal to the 0 vector for all alpha in F. 3. If alpha v is equal to the 0 vector, then either alpha is equal to 0 or v is equal to the 0 vector. 4. Negative 1 times v is equal to negative v for all v in v. Note here that this allows us to transition between the abelian group of the field and the abelian group given by the vector space, and the inverses thereof. 5. Negative alpha v is equal to negative alpha v is equal to alpha negative v for all alpha in F and all v in v. Proof. To prove 1, observe that 0v equals 0 plus 0v equals 0v plus 0v, and consequently 0 plus 0v is equal to 0v plus 0v. Since v is an abelian group, 0 is equal to 0v. The proof of 2 is almost identical to the proof of 1. For 3, we are done if alpha is equal to 0, so suppose that alpha is not equal to 0. Multiplying both sides of AV equals 0 by 1 over A, notice here that this is where we require that our element is a field. We have that V is equal to 0. To show 4, observe that V plus negative 1V equals 1V plus negative 1V equals 1 minus 1V equals 0V equals the 0 vector. And so negative V is equal to negative 1V. We will leave the proof of 5 as an exercise. 20.2. Subspaces. Just as groups have subgroups and rings have subrings, vector spaces also have substructures. Let V be a vector space over a field F and W a subset of V. Then W is a subspace of V if it is closed under vector addition and scalar multiplication. That is, if U and V are in W and alpha is in F, it will always be the case that U plus V and alpha V are also in W. So, for example, 20.6. Let W be the subspace of R cubed, defined by W is equal to x1, 2x1 plus x2, and x1 minus x2 for x1 and x2 in R. We claim that W is a subspace of R3, since alpha x1, 2x1 plus x2, x1 minus x2, equals alpha x1, alpha 2x1 plus x2, alpha x1 minus x2, and then distributing we get equals alpha x1, 2 alpha x1 plus alpha x2, alpha x1 minus alpha x2. W is closed under scalar multiplication. To show that W is closed under vector addition, let U be equal to x1, 2x1 plus x2, x1 minus x2, and V be equal to y1, 2y1 plus y2, y1 minus y2 be vectors in W. Then we have this horrible distributive thing. For those who know linear algebra a bit more, another way you can say is that we have a homomorphism we have a linear transformation from R2 into this space such that the image is W, and the image of a homomorphism is always a vector subspace. So this also is an equivalent way to show that it's a subspace. Because personally, I think of that much easier than the direct computation. Example 20.7. Let W be the subset of polynomials of f of x with no odd power terms. If p of x and q of x have no odd power terms, then neither will p of x plus q of x. Also, alpha p of x is in W for alpha in F, and p of x in W. Now, let V be any vector space over a field F, and suppose that v1, v2, all the way to vn are vectors in V, and let alpha 1, alpha 2, all the way to alpha n be scalars in F. Any vector W in V of the form W is equal to the sum from I equals 1 to n, alpha I vi, which is written as alpha 1 v1 plus alpha 2 v2 plus all 1 plus alpha n vn, is called a linear combination of the vectors v1, v2 to vn. The spanning set of vectors v1, v2 to vn is a set of vectors obtained from all possible linear combinations of v1, v2, vn. If W is the spanning set of v1, v2 to vn, then we say W is spanned by v1, v2, vn. Alright, so one way to write this, is basically saying we're given some vectors and we're allowed to, W is a collection of all vectors that are the, scalar multiplications, the linear combinations of these, because we're letting the alpha i's be arbitrary scalars in this. But the vi's are fixed. Proposition 20.8. Let S be equal to v1, v2, all the way to vn, be vectors in a vector space V. And the span of S is a subspace of V. Proof. Let U and V be in S. We can write down both of these vectors as linear combination of the vi's, as U is equal to a1 v1 plus a2 v2 all the way to an vn, and V is equal to b1 v1 plus v2 v2 all the way to bn vn. Then, U plus V is equal to alpha 1 plus beta 1 v1 plus alpha 2 plus beta 2 v2 plus on and on all the way to alpha n beta n vn, which comes from this little thing right here, that little axiom right there. Then we have, the linear combination is a linear combination of the vi's. For alpha in F, alpha u is equal to alpha 1 v1 plus alpha 2 v2 plus on and on plus alpha n vn is in the span of S. Notice how we used both distributivity properties of this, and you can think of the definitions of the vectors, like a definition of a vector space, in part by wanting to make sure that this actually holds. That taking linear combinations and their spans gives us subspaces to do analysis on. 20.3. Linear independence. Let S be equal to v1, v2, all the way to vn be a set of vectors in a vector space V. If there exist scalars alpha 1, alpha 2, all the way to alpha n in F, such that not all the AI's are 0, and alpha 1 v1 plus alpha 2 v2 plus on and on 2 plus alpha n vn is equal to the 0 vector, then S is said to be linearly dependent. If the set S is not linearly dependent, then it is said to be linearly independent. More specifically, S is a linearly independent set if alpha 1 v1 plus alpha 2 v2 plus on and on 2 plus alpha n vn is equal to the 0 vector, implies that alpha 1 is equal to alpha 2 is equal on and on 2 equal to alpha n equals 0 for any set of scalars alpha 1, alpha 2, all the way to alpha n. So what it's basically saying is that these vectors form a basis, in the sense that you can't represent one vector as a combination of the others. Each vector adds new information to this. So for example, let me bring these axioms to the side for a little bit to discuss, to talk about this. So if we have the coordinate plane R2, right? And we have these two vectors, v1 and v2. Well, obviously, the only thing we can get from v1 would be by scaling it in either direction, and v2 would be scaling this. We can't get v1 by multiple v1 as we can't multiply v1 by something non-zero and add it to get v2 times something, as long as that thing isn't 0. What it's saying is that there's fundamentally different information contained in here. But now let's add this vector v3. Well, v3 is a certain alpha v2 or alpha 2 v2 along with alpha 1 v1. And since we can write v3 in terms of the sum of alpha 1 v1 and alpha 2 v2, that means that v1, v2, and v3 are not linearly independent. There's some redundant information here. Alright, give me a second to drag this back. Alright. Proposition 20.9. Let v1, v2, all the way to vn be a set of linearly independent vectors in a vector space. Suppose that v is equal to alpha 1 v1 plus alpha 2 v2 plus on and on plus alpha n vn is equal to beta 1 v1 plus beta 2 v2 all the way to plus beta n vn. Then alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, all the way to alpha n is beta n. So it basically says that if we have a linearly independent vector, a linearly independent set of vectors, then if a vector is equal to a sum of those vectors, that sum is unique in terms of the coefficients. Proof. If v is equal to alpha 1 v1 all the way to the sum of alpha i's vi's is equal to the sum of the beta i's vi's, then alpha 1 minus beta 1 v1 plus alpha 2 minus beta 2 v2 plus on and on to plus alpha n minus beta n vn is equal to 0. Since v1 all the way to vn are linearly independent, alpha I minus beta I equals 0 for I equals 1 to n, which implies that alpha I is equal to beta I. Again, constantly I'm going to keep reiterating this. Note how required the distributivity of this has to be in order to make these proofs work. The definition of linear dependence makes more sense if we consider the following proposition. Proposition 20.10. A set v1, v2, all the way to vn of vectors in a vector space V is linearly dependent if and only if one of the vi's is a linear combination of the rest. So proof. Also, before I say this, I'm going to note that this comes from the fact that we have a field that we're working over. You can already see the divisions. So if you're working with modules, which are basically the same axioms, but we replace field with just ring, this actually will not hold true. In fact, there are some differently ambiguously defined bases. Alright, proof. Suppose that v1, v2, all the way to vn is a set of linearly dependent vectors. Then there exist scalars alpha1, alpha2, all the way to alpha n, such that alpha1 v1 plus alpha2 v2 plus on and on to plus alpha n vn is equal to the 0 vector, with at least one of the ai's not equal to 0. Suppose that ak is not equal to 0. We can assume this because there's only finitely many of them, so we can pick out a specific ak consistently. And as well, we already know that one of them is not equal to 0, so we have to have 1. Then vk is equal to negative alpha 1 over alpha k v1 minus on and on minus alpha k minus 1 over alpha k vk minus 1 minus alpha k plus 1 over alpha k vk plus 1 on and on to minus alpha n over alpha k vn. So this is very wordy. What does this mean? Basically, we take this term, we subtract vk on both sides, and then we divide by negative a sub k, which is how we're getting this entire expression and why we're missing the vk in this part of the sum, because the vk got moved from this part of the sum to this. Conversely, suppose that vk is equal to beta 1 beta v1 plus on and on to plus beta k minus 1 vk minus 1 plus beta k plus 1 vk plus 1 plus on and on to beta n vn. Then beta 1 v1 plus on and on to plus beta k minus 1 vk minus 1 minus vk plus bk plus 1 vk plus 1 plus on and on to plus bn vn is equal to the 0 vector. The following proposition is a consequence of the fact that any system of homogeneous linear equations with more unknowns than equations will have a non-trivial solution. We leave the details of the proof for the end of chapter exercises. So suppose that a vector space V is spanned by n vectors. If m is greater than n, then any set of m vectors in V must be linearly dependent. A set E1, E2, all the way to En of vectors in a vector space V is called a basis for V if E1, E2, all the way to En is both a linearly independent set and that set spans V. So for example 20.12, the vectors E1 equals 1, 0, 0, E2 equals 0, 1, 0, and E3 equals 0, 0, 1 form a basis for R3. The set certainly spans R3, since any arbitrary vector x1, x2, x3 in R3 can be written as x1 E1 plus x2 E2 plus x3 E3. Also, none of the vectors E1, E2, E3 can be written as a linear combination of the other two, hence they are linearly independent. The vectors E1, E2, E3 are not the only basis of R3. The set 3, 2, 1, 3, 2, 0, and 1, 1, 1 is also a basis for R3. As well, example 20.13. Let Q be equal to let Q adjoin square root of 2 be equal to A plus B square root of 2 with A and B in the rational numbers. The sets 1 square root of 2 and plus square root of 2, 1 minus square root of 2 are both bases of Q root 2. From the last two examples, it should be clear that given a vector space, the space has several bases. In fact, there are an infinite number of bases for both of these examples. In general, there is no unique basis for a vector space. However, every basis of R3 consists of exactly 3 vectors, and every basis of Q adjoin 2 consists of exactly 2 vectors. This is a consequence of the next proposition. So proposition 20.14. Let E1, E2 all the way to Em, and F1, F2 all the way to Fn be 2 bases for vector space V. Then M is equal to N. Proof. Let E1, E2 all the way to Em be a basis, and since it is a basis, it is a linearly independent set. By proposition 20.11, N is less than or equal to M. Similarly, F1, F2 all the way to Fn is a linearly independent set, and the last proposition implies that M is less than or equal to N. Consequently, M is equal to N. So this is because it's comparing the two and asking like, hey, what linear combinations of stuff in E1 gets us to F1, gets us to F2, gets us to Fn? And because of linear independence result and proposition 20.11, which I've put as an end of chapter exercise, because we want to imply that they're not linearly dependent, we have these inequalities bounded because we know they are linearly independent because they're bases. Excuse me. Yeah. If E1, E2, all the way to En is a basis for a vector space V, then we say that the dimension of V is n, and the right dimension of V is equal to n. We will leave the proof of the following theorem as an exercise. Oh god, I'm already looking down. Is that the reading questions already? Is this chapter already nearly done? Theorem 20.15. Let V be a vector space of dimension n. 1. If S is equal to V1 all the way to Vn is a set of linearly independent vectors for V, then S is a basis for V. 2. If S is equal to V1 all the way to Vn spans V, then S is a basis for V. 3. If S is equal to V1 all the way to Vk is a set of linearly independent vectors for V with k less than n, then there exist vectors Vk plus 1 all the way to Vn, such that V1 all the way to Vk, Vk plus 1 all the way to Vn is a basis for V. Sage. Nan, not worrying about Sage. So, why do the axioms of a vector space appear to have only 4 conditions, rather than the 10 you may have seen the first time you saw an axiomatic definition? This comes from the fact that, since we now have the tools of linear algebra to talk about, and we're not just talking about the real numbers, we're able to, since we have an abelian group inherently defined in both of the structures, we don't need to specify that extra information for it. For example, we don't need to specify that v plus w is equal to w plus v, because we already have that in the assumption that v is an abelian group. So basically, the extra assumptions we have on top, the fact that we have both a field and an abelian group, substitutes the previous definitions one would have. So the set V equals Q squared 11 equals A plus B squared 11. AB is a vector space. Carefully define the operation on this set that will make this possible. Describe the subspace spanned by S equals squared U, where U, give me a second. Alright, my bad. Describe the subspace spanned by S equals U, where U is equal to 3 plus 2 over 7 squared 11b. Alright, so let's get rid of these. Actually, I'll only put them to the side. Alright, the set V, A plus B root 11. So I'm assuming what it is we'll define A plus B square root 11 plus C plus D square root 11 to be equal to A plus C plus B plus D square root 11. This is how we'll define addition. And from the looks of it, the only reasonable way to define multiplication would be that n of, or yeah, I'll just use p for an arbitrary rational number. A plus b square root 11 is equal to pa plus pb squared 11. Alright, does this work? So we have associativity inherent in the associativity of this. We have distributivity, correct? Yes, we have distributivity. We have distributivity in both of those. And we have that 1 times v is equal to v. Yeah. Mainly because you can think of it in terms of, it's a fancy way of, the square root 11 in this case doesn't particularly matter. It's more so that we just have a two-dimensional real vector space, AB, and given a two-dimensional, or well, a two-dimensional rational space, or a space that's isomorphic, at least as an abelian group, to Q squared, we have a natural, like, Q multiplication on that to make it into a Q vector space. Alright, and then describe the subspace spanned by S equals U, where U is equal to 3 plus 2 over 7 square root 11. This is just going to be equal to the set of all multiples of this. So for example, every num wait, is this what I'm thinking? That's bizarre. Okay. So this will actually span a subspace that has irrational entries. That it like every element of that subspace is irrational. Oh, that is weird. That is really weird. Okay. These two are right long paragraphs, and linear algebra is all about linear combinations. Explain why you might say this. Um, because it's obvious. We define linear combinations. Define linear combinations. Define linear independence. Linear combinations define like using coordinate-wise bases, and then later on we'll use linear transformations. Will be defined in terms of like we'll have other things associated with them for linear stuffs. So yeah, linear algebra is all about linear combinations. All right, these look like some. These are some spicy problems. Okay, I'm going to give these, especially now. I'm just gonna say this problem. I didn't do it when I first did it, and I really regret that I didn't do it because oh my god, it is like essential. All right, all right. But before we get into that, our regularly scheduled intermission. Alright, I'm back. I'm ready to go. And I've got some coffee to boot, so let's get to it. Alright, if f is a field, show that f of x is a vector space over f, where the vectors in f of x are polynomials, vector addition is polynomial addition, and scalar multiplication is defined by a p of x for a and f. Alright, so we basically need to check the properties. First of all, we know that f of x is an abelian group because f is an abelian group as well. So we know that the abelianness condition of the thing is satisfied. To show that it's associative, we'll have a times the sum of I'll use some indirect notation. Beta I x to the I. But yeah, we need to show alpha times c of that. Oh, that's horrible. But you know what, we're gonna go with it. Which is equal to alpha times the sum of c beta I xi is equal to the sum from I thought this was a parenthesis for a second. AC beta I xi is equal to AC sum beta I xi. So we have the associativity multiplication, alpha plus beta v. So we have alpha plus beta of sum ci xi. Oh, I'm switching up my notation all over the place, which is the sum of alpha plus beta c xi by the fact that we have a ring structure, the field structure. We have its alpha c plus beta, alpha c xi plus beta c xi. I should also put a subscript for the I. Oh, I could introduce some Einstein notation stuff if I want to, which is equal to the sum from alpha ci xi plus the sum of beta ci xi. Take this, knock it up, to get, oh gosh, what is it? My brain is failing me right now, please. Okay, is equal to alpha sum ci xi plus beta sum ci xi. Alright, so that shows the distributivity of the scalar multiplication. And also, I'm just going to leave this like the vector addition and the distributivity of that. Of scalars, it's kind of obvious, and then the one value, we just have 1. And under this identification, since 1 times ci is equal to ci, then we have 1 times v is equal to v. So yeah, prove that q root 2 is a vector space. So suppose we have q root 2, so suppose we have, first of all, a plus q adjoint root 2 is already an abelian group, because q root 2 is actually a field, so, I mean, the fact is, what we could do is, as an abelian group, note here I said as an abelian group, here's a better way to do this. So we have q adjoin root 2, and we have an isomorphism to q squared, which is given by phi of a plus b of root 2 is equal to phi is equal to a b. Note here, I'm gonna put in massive red letters. Group. It is important to notice in this that this is not at all a ring isomorphism, not even close. This is just a group isomorphism. However, the nice thing is that it's an abelian group homomorphism. So what we do is the structure that was given is the vector space structure on Q2. And from that, what we do is we bring the vector space structure back over here by just a relabeling of the elements. And then that's exactly what we do. And since this has a vector space structure, and we bring this back, then we have our regular vector space structure. So more succinctly, we can say, suppose we have abelian groups A and B that are isomorphic as abelian groups. So I'll have phi abelian homomorphism or abelian isomorphism. And suppose that these are and suppose that B has a vector space structure given over F. B is a vector space over F. Vector space over F. Now define a vector space structure, define a product from F times A to A, and it will be given by this. We'll first transfer A to B, apply the operation in B, and then transfer B back to A. So explicitly defining this, we have, we'll call it F A will be equal to phi to the negative 1 F of phi of A. What this is it takes A, moves it to B, applies F, and moves it back. And now what we want to say is that given this, we have that A is a vector space. So A is a vector space over F. Vector space over F. So let's actually prove this. Let's move to the working board. Let's move to the working board to prove this because this is actually slightly different than what's being asked. So working board. All right. So these are the axioms. I'm going to bring these axioms of the group to the side of the screen to remind us what we need to do. So first of all, we need to show associativity. So let F G, this is, okay, let's do this. So we have A, B of V. So A of B of V is equal to A times phi to the negative 1 times B of phi of A, or of V. So this is a whole thing in and of itself. So then we have that this is equal to phi to the negative 1 times A of phi to the negative 1 of B of phi of V. However, these two, because they're their inverse functions, cancel each other out. So this is equal to phi to the negative 1 A B phi of V. Now, because B is a vector space over F, we have the associativity rule here. So we have this is equal to phi to the negative 1 AB times phi of V, which is just equal to AB of V. So we have this. Let's check these off. And yeah, I might as well just do the full rigorous details just to make absolutely sure I know what's going on. So from here we have, let's get rid of this. So now, we want to show that A plus BV is equal to AV plus BV. Also, I should quick put, you know what, I'm going to do like another color or something. So check mark. So alpha plus beta V. So A plus B of V is equal to phi to the negative 1, a plus b phi of v is equal to phi to the negative 1. Oh, this is where we actually have to use some more subtle facts. A phi of v plus b phi of v. And this is where we have to use the fact that we have an isomorphism. Because the homomorphism is equal to phi to the negative 1 a phi of v plus phi to the negative 1 b v of v is equal to a v plus bv. So we have that this right here, check that off. So now we have AV plus W is equal to AV plus AW. So we have A of V plus W. So we have, this is phi to the negative 1. You can already probably tell, it's going to be basically the same thing, except we swap out the A and the V plus W. So I'm just going to count that as completed then, because the only other thing we need to actually ensure is fairly easy. So we want to ensure that 1 times V is equal to V. So we have phi to the negative 1 of 1 V is equal to v negative 1 V VV. By our assumption, we have that is equal to phi to the phi of V is equal to V. So this basically says that this proves a theorem that if, oh gosh, I should probably more carefully erase the check marks there so I don't get confused later on. So it basically is that if we have some isomorphism between abelian groups, because remember, we need our group fundamentally to be abelian, so we need our just assumption that it's abelian. It's an abelian isomorphism, and B is a vector space over B. Then we can define B is a vector space over F. Then we can define A as a vector space over over F. A is a vector space over F by defining a dot where we take an element to B, apply it, and then bring it back. So let's actually use this to prove let's go back to standard textbook and let's actually prove this. So is really isomorphism. So A is a vector space over B. Alright, so we take this over, I'll keep this in the corner. So we want to make in a V a vector, so we want to, it shouldn't be green, that was my bad. So we want to define a abelian group homomorphism between A square root of 2 and Q2. And we'll define it by A plus B square root of 2 is equal to phi of A B square root of 2 is equal to AB. First of all, it should be clear that because we're working over the rationals, it is injective. Alright, so yeah, okay. It's obviously surjective, and it obviously obeys the group operation because of the fact that square root of 2 is irrational. And so is it injective? So because if phi of A plus B square root of 2 is equal to 0, then A and B both have to be 0, so this has to be 0. So we form a vector space here, right? So we form a group isomorphism here. Now from here, we define the vector space structure by C times A B is equal to CA is equal to CA CB. And I'm not going to completely go through it, but it should be very obvious that this is a vector space, right? It should be very obvious this is a vector space over the rationals. So let's compute we might even call it something like the pullback vector space, because we're pulling back a vector space from B onto A. So we'll define C of A plus B root 2 to be equal to phi to the negative 1, C of phi of A plus B root 2, which is equal to phi to the negative 1 of CA plus CB square root of 2. Oh, wait, yeah. Is equal to, yeah. C times A, B. Let me shrink all this up here. Is equal to phi to the negative 1 of CA, CB, and I'll write it over here, is equal to CA plus CB square root of 2. And because we proved it in full generality, this shows that we don't even need to check the axioms on this specific vector space. All we needed to show that there was a vector space structure over Q squared, and that Q adjoined root 2 as an additive group is isomorphic group-wise to Q adjoined to Q squared, and that its structure was described by what was given in the theorem. Oh, that is really satisfying. I've never actually proved that before, but like I saw this and I'm like, I feel like there's like a pullback thing you can do, because you're basically treating it as like two bases vectors, so it might as well be the quote-unquote free basis, or the free vector space on the basis of two elements. But I'm getting ahead of myself. All right, so like Q square root 2 square root of 3 be the field generated by elements of the form A plus B square root 2 plus C square root of 3 plus D square root of 6, where A, B, C, and D are in Q. Prove that Q square root of 2 square root of 3 is a vector space of dimension 4 over Q. Find a basis for Q square root of 2 square root of 3. So what we can do is, first of all, we can use our previous lemma. That lemma is actually extremely powerful now. So what we want to do is we want to show that phi of A plus B square root of 2 plus C square root of 3 plus D square root of 6 is equal to, we define that to be A, B, C, D in Q to the 4. It's a vector space. So we have, if we ensure that this is if we can ensure that this is a isomorphism of groups, of abelian groups, then we have automatically the pullback vector space structure. So for this, obviously it's surjective. Is it injective? So basically, can we write square root of 2 or square root of 3 or square root of 6 in terms of a linear combination of the others? So suppose that square root of 2 is equal to A plus C root 3 plus D root 6. Then we square it to get 2 is equal to this element squared. Is equal to A squared plus A C root 3 plus A D root 6 plus we have A C root 3 plus C squared times 3 plus C square root of 3 times square root of 6. So we have 3 C D square root of 2 plus basically a ton of terms like this. And what this implies is that basically we need a lemma that if... I'm trying to think of how to write this. So like, first of all, square root of 2 is square root of 2 equal to c square root of 3 plus d square root of 6. Because if this is true, then our map is not injective. Or actually, I don't even know if it would be well defined in that case. Alright, so square root of 2, so we square that, and we get c squared 3 plus 2 times cd square root of 3 is equal to, that's 3 times 2, so it's 3 square root of 2 plus d6. Plus d squared 6. Well, obviously, both c... Oh! Alright. So if both c and d are non-zero, then this will be an irrational number, and a rational number can't equal the sum of... A rational number can't be the sum of irrationals with rationals, or an irrational with rationals, so that can't be true. So either c or d equal to 0, but if that's the case, then one of these two have to be like an integer, but that would imply that we have the square root of 2 as a rational number, which is impossible, which means that this is actually a completely linearly independent set. So these terms can't be written as a combination of each other, so it's both surjective and injective, and it obviously respects the group composition, so it is a proper like isomorphism of abelian groups, at least additively. Which means that, oh god, I love this. Which means that writing this out gives us the leverage to use the first of all, this is dimension 4, so we have a pullback vector space. And because the vector spaces are isomorphic, I think later on it will ask us to verify this. We can pull back the bases, and we'll get bases of that, and we'll get uniquely 4 basis elements. Which means that this will also have a vector space structure of dimension 4. Ah, that is so cool. Oh, I love that. Okay. Okay. So like we can define like the dimension as a 1, square root of 2, square root of 3, square root of 6. Alright, prove that the complex numbers are a vector space of dimension 2 over R. It's mainly that we can make an additive isomorphism between C and R squared. It's going to be the same thing, so I'm not going to reiterate it. Prove that the set Pn of all polynomials of degree less than n form a subspace of the vector space f of x. Find a basis for P of n and compute the dimension of n. Alright, less than n is... This is going to have dimension n minus 1. Since we can just let it be 1x squared all the way to xn minus 1. Because it's degree less than n. And then adding them together will give us another element in the span. Yeah. Alright, let f be a field and note the set of n tuples, given the vectors, find vector addition by that, scale multiplication by that. Yeah. So this is obvious, so I'm not going to prove it, but this is like foundational to our previous result. Both the isomorphism and this result gives us like along the pullback vector space, because they are now isomorphic vector spaces, gives us all the nice results of classification. So which of the following sets are subspaces of R3 if the set is spanned by a subspace? Oh gosh. So let me solve, I'll just solve 7a because I'm very lazy. So we have the space spanned by, so we have 3x1, we have 3x1, minus 2x squared plus x3 minus 2x2 plus x3 is equal to 0. 3 is equal to 0. So what this is basically saying is that 3x1, or we can basically say that x1 is equal to negative 2 over 3 x2 plus 1 over 3 x3. And the nice thing about this is that these are like completely independent definitions. So now let's define a transformation. I'm saying this now and I'm not going to prove it much because we're going to be literally proving it later. So t from r squared to r cubed given by, here's some indicative notation, x2, x3 is equal to negative 2/3 x2 plus 1/3 x3, x2, x3. The image is obviously the space spanned out in the problem definition, and because the image is a subspace, this means that it is indeed a subspace. We can write a linear transformation according to it, because subspaces correspond directly to linear transformations. Alright. At least under certain choice considerations. We're not worried about that now. Show the set of all possible solutions of x, y, z, y squared, the equations form a subspace of. Show the solution of set of all possible solutions of ax plus by plus cz. And dx plus ey plus cz is. I don't know if this is supposed to be a c or is this supposed to be an f. But I'm not gonna worry about it because I'm lazy. Alright, from subspace of R3. It's gonna be a simple linear transformation matter as well. So let W be the subset of continuous functions that f0 is equal to 0. It's mainly that like scaling by a value or adding a value at that point for that function will be still equal to 0 at that, so it doesn't matter. 11, prove that negative AV. V vector space, prove that negative AV equals negative A equals negative V for all V. So, okay. So I want to prove that negative AV, so like a negative AV plus AV so we want to show, alright, negative AV plus AV is equal to 0. Oh gosh, let me think. So we now have negative AV minus. Okay. Wait, negative AV. We want to show that negative AV is equal to negative 1 AV. That's probably the simplest thing we can do in this. So we basically show that negative AV is equal to negative 1 AV. So negative AV plus 1 AV is equal to negative AV plus AV is equal to 0. So this inequality naturally follows. So then we have negative AV plus AV. So then we have negative 1 AV plus AV to get negative 1 plus 1 AV AV is equal to 0 to get, is this showing inverses for all of them? Oh, this problem's lame. Nah, I'm feeling lazy. I'll leave the rest of the details as a computation. Alright. Let V be a vector space of dimension n for each of the following statements. If S is equal to V1, V all the way to Vn is simply S spaces for n. So if dimension n So what I'm thinking is, first of all, we'll do this. So suppose we have a linear equation. Suppose we have an equation. We have v1, a1, v1. Alright, so we have, okay, let me put it more carefully like this. Alright, the sum. So we have equation 1, which is the sum from the sum. Suppose we have, okay, a sum of a, sum of a, I1, vi is equal to beta 1, sum of ai 2 v of I is equal to beta 2. Or actually, because it's going to be, yeah, because we can write, just include it, we're going to have this. First of all, suppose they're all equal to 0, and suppose we have sum of a I m vi. So we'll note here that we'll have here from I goes to 1 to n is equal to 0 for n greater than, for n, or no, m greater than n, right? For m greater than n. So we want to show that this has a non-trivial solution in terms of the VIs. So we can have VIs be positive values. So, okay. Yeah. So in each of these, we have that sum AK. We have sum AK of j is not equal to 0 for each j. And we want to show that this has a non-trivial solution of, like, we have possibly that not all vectors are equal to 0. So let's do this by induction. Alright, so first our base case, our case where n is equal to 1. So suppose we have, also as well, notice that if we have, for this, if we can prove the case where it's n plus 1, then we prove the case for all m greater than it. Because then we can just like reduce the first n plus 1 equations, and it's at least n plus 1. So suppose we have a1. So we have like a1 v1 is equal to 0, and we have a2 v1 is equal to 0. So we have two equations with one unknown. So I is equal to 1. So we have that a1 v1 is equal to a2 v1. So we have that a1 minus a2 v1 is equal to 0. Wait, no, that isn't right. Okay. Wait, I need some more assumptions. I'm being dumb. Alright. Let's think about the problem at hand instead of immediately jumping ahead. Alright, so if S of v1 all the way to vn is a set of linearly independent vectors for v, then S is a basis for v. So suppose v has dimension n. So dimension of v is equal to n. V equals n, which means that it has a basis e1 all the way to en. And suppose that S is basis equals v1, but S is the basis friend. So we have a set of linearly independent vectors, so like v1 all the way to vn. We have basis, we have that. And we want to prove that v1 is basis. So we have that this is linearly independent. So suppose that this is not a basis. Then this means that there's some element, there's some vector, delta I. Yeah, there's some vector, delta I, not in span of, let's call this S for now, not in the span of S. Which means that we can form, or we can, instead of calling this delta I like an absolute, not smart, we have vn plus 1 is not in the span of S. Which implies that adding vn plus 1, appending vn plus 1, gives us a linearly independent set of v1 all the way to vn plus 1. Right? Now set up the linear equations. Alpha alpha 1 e1 plus alpha 2 e2 plus on and on. Because we have a basis, we have that for each of these, we have alpha n, or we have the I equations of the form alpha n is equal to en is equal to v sub I, where 1 is less than or equal to I is less than or equal to n plus 1. With all these equations being non-trivial. So let's think here. So we have greater equations than unknowns, right? So, oh gosh. And since we have greater equations than unknowns, alright, I think what it's supposed to be, now that we have this, what we do is we can write, because of this, as vn, since v n plus 1, oh wait, yes, okay. Now we need to determine, so we have vn plus 1 is equal to this thing, and we need to be able to determine the equations, the coefficients. Okay. So let's switch to the working board for some inspiration. Oh man, I'm having way more trouble with this than I was expecting. So suppose we have, like, for example, ax is equal to b, or ax is equal to y. Where y is constant, or I should write ax is equal to c, and bx is equal to c. Or c prime. Then we have ax minus c is equal to bx minus c prime. So we can write a minus b of x is equal to c minus c prime. So we have that x is equal to c minus c prime over a minus b. So what we can do is this allows us to determine the vector. If we consider this as vectors, let's consider these, like, give them little vector hats. What this means is that if we have more equations than we have unknowns, basically applying this process inductively gets us a way to solve for a vector in a non-trivial way. Oh, I think I'm starting to get it now. I think I'm starting to understand it. So we have it. These are all non-zero. It's important to note that these are all non-zero. So first of all, okay, I think we can restate the lemma I want to prove. So suppose we have m equations, or actually we only need to worry about n plus 1 equations and n unknowns that we want to solve for, with coefficients already given. Then there will be a non-trivial solution. So let's write it out. So for the case that it's equal to 1, we have a x bar is equal to c, and we have a x bar is equal to c, c bar, and we have b x bar is equal to d bar, which then dividing, because we have a field, we have x bar is equal to a over 1 over a c bar. X is equal to 1 over a c bar. So we have n unknowns. So we want to solve for x. So we have 1 unknown and 2 equations. Wait, I'm trying to think. No, I want to solve for the coefficients, I'm pretty sure, right? Wait, I'm getting confused. About all this. I have not done linear algebra in long enough. My brain is having a moment. Alright. I'm going to step back from this problem for a quick session, make sure my Twitch is doing, like, alright, and take a sip of coffee. Okay. So we have these equations. For ones, let's go to I. I should also probably put a coefficients on this, so boom. So what we want to do is we want to show that if V doesn't span S, and we have n plus 1 equations with that many coefficients, many unknowns. So like basically what we can do, I guess one way to show this is suppose we have a E1. So let's do a simple case. So a E1 is equal to V1 and a E2 is equal to V2, right? A1 is equal to that. Then we can factorize a E1. Since A1 is equal to V2, we can define E1 is equal to 1 over a V2. Right? So then we can write this as I should write this as a prime, 1 over a prime. So we have a 1 over a prime V2 bar. I think I get it now. Okay. So a plus V2 minus 1 over a v1 bar is equal to 0. Yes, okay. So from here, what we have is that these coefficients are both non-zero. So we have the non-zero sums of two vectors being equal to 0, which means that it's not linearly dependent. And we need to show that this is always the case when we have more unknowns. So this basically, this equation right here, and the fact that it's a field, shows that this is the case for n equals 2. So suppose that's the case for up to n, right? So suppose we have, so a1 I e1 bar plus blah 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 plus a of n I e to the n bar is equal to v bar I. We have I equations of this form. Actually, I wrote this down here, but I'm giving myself more space to work on this. So we have I equations of that form. So what do we get out of this when we're solving this as a system of equations? Let's think carefully. Play the Phoenix Wright music inside of my skull. Okay, so we have from here, this allows us to write E1. This allows us, yes. So we have n plus 1. So what we can do is, let's take the case A1 to use an inductive hypothesis. A1 n plus 1 E1 bar plus blah 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 plus yes, okay, I'm getting it now. All the way to a oh gosh. Oh wait, actually yeah, this is right. A n plus 1 e n is equal to vi. So we have this. This means that we can write, we can take this and we write it as en bar is equal to vi bar plus a n minus 1 n plus 1 e to the n minus 1 bar plus blah 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 plus a1 n plus 1 e n plus 1 bar, all divided by 1 over a n plus 1. Oh wait, actually this is included in the brackets. Excuse me, I'm being a bit silly right now. So this is included in that, right? Which allows us to, from here, first of all, this number is non-zero. So we can go back to all the previous equations and make, so we have n total equations, so then we can make n minus 1 total equations, where it's of the form, oh gosh, the sum, okay, this is going to be weird, sum from I equals 1 to n minus 1 of a sub I j e to the I plus the sum of this, which we'll call S, minus v bar I 1 over a blah 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 1 over a, yeah, a n plus 1, to just cancel it out, So this basically means that in this term, we're going to be having this horrible sum up here, except we won't be having this vi. And that takes us into a linear expression is equal to vj bar minus v bar I 1 over an n plus 1. Since these are linearly independent, we know this term is not going to be equal to 0. And as well, when we actually simplify these terms out, we get an expression of n minus 1. Yeah, we get we have n equations here. And we have, because of this subtraction, because we've replaced en, of n minus 1 variables. So using the inductive hypothesis, we know that this set actually isn't linearly independent, the set of the remaining. But that should be impossible, considering like we've subtracted by vj and we removed vj from the span, which shows that this set must span all of S, because otherwise we would get a linearly independent set. Which means that since we already know this is linearly independent, it shows us that it's a basis. Oh my gosh, okay. This is one of the times where I probably should have something where I can like open a LaTeX file. Because that was like horrible to write down on paper. Okay. Oh my gosh, okay. If V spans V, then S is a basis for V. Yeah, so if this is not linearly independent, it implies that since it spans V, there is some basis of dimension less than that, which contradicts what it means to have a dimension. Because we can write our actual dimension thing and then use the previous argument to show that like the basis is not linearly independent, which is a contradiction. If that is a set of linearly independent vectors, okay, that is a basis for V. You can just do an algorithm, kind of like I showed earlier, if you take something in the span and you take it requires axiom of choice in a lot of scenarios, but you produce something, or I probably could use, oh no, that's only if you have a Hilbert space, a Gram-Schmidt, or orthogonalization process. Oh god, no, wait, I'm forgetting Gram-Schmidt. You basically choose something that's not in the span at each point, and eventually you'll choose a basis by that process because it's not in the span, so it's linearly independent. And then from there, you'll have that... excuse me. You'll ultimately have... My brain is not working right now. Oh gosh, I really am forgetting. Shoot. Not good. Okay. Basically, in each one of these, you'll expand something. If it's not in the span, it'll be linearly independent. And ultimately, once we get to Vn, because it will be a basis of Vn, because otherwise it would go above, and then you would use the same argument as we wrote out painfully in part A. Okay. Prove that any set of vectors containing zero is linearly independent. Multiply the zero vector by literally anything. Let V be a vector space. Show that U is a subspace V of dimension 0. Because if it has a basis, then it has the set 0, but the set 0 is not linearly independent, so it's dimension 0. 14. If a vector space is spanned by n vectors, show that any set of m vectors must be linearly dependent for m greater than n. This is the same kind of argument it was talking about proving later. But I'm going to skip that for now. Okay. This is... Gosh, I did not expect to be doing so much math on this chapter. I did not expect me to be like as hyped about this as I was. Alright, linear transformations. Let V and W be vector spaces over a field F of dimensions m and n respectively. If T from V to the V to W is a map satisfying T of U plus V equals T of U plus V of W, so I'm going to write this down here. So T is a map from V to W. Though we express both expressions by saying A, V plus B, W is equal to A, T of VW, plus B, T of W. We ultimately express it as that, for simplicity's sake. Then T is called a linear transformation. prove that the kernel is a subspace of V. The kernel of T is sometimes called the null space of T. So the kernel, so assume that U, first of all, assume that U, T of U is equal to 0. T of U is equal to 0. Then T of AU is equal to A T of U is equal to A0 is equal to 0. So AU is in kernel of T. And we have that T of U plus V for U and V in kernel is equal to T of U plus T of V. And since they're both in the kernel, it's equal to 0 plus 0 is equal to 0. So U plus V is in the kernel. So the kernel is a subspace. Alright, the range space is a subspace of W. I've been using this result, so time to actually prove it. So if W is equal to T of V, then AW, note that these are both vectors fields over the same field F, by the way, before I get into this. Then AW is equal to A T of V is equal to T of AW, or AV. And the reason I mention this is that otherwise this multiplication doesn't make sense. So we have that. So we show that, and then W plus V is equal to T of W prime plus T of V prime, switching up the notation randomly on you, is equal to T of W prime plus V prime. So it's a subspace. And that's commonly like one of the examples I'll use to show that it is a subspace. And you've seen me use it previously, is that I'll show there's a linear like map between two spaces with the image being the set or the kernel being the set. And then that shows that that set is actually a linear subspace because it's the kernel or image of a map. It's kind of like showing that a group is a like subgroup by use of the image or kernel in a group homomorphism. It's actually exactly like that. Show that TU is injective if and only if kernel of T is equal to 0. So if kernel of T is not equal to 0, there's some vector V in it that's not equal to 0. Alright, we actually, yeah. Let's write this. So, yeah, okay, actually, first, alright, so if T of V is equal to 0, T of V plus V is equal to 0, which means T of V is equal to T of V plus V, which is only, this is, which implies that if V is not equal to 0, V is not equal to 0, T is not injective, T is not injective as well. If T of V is equal to T of W, then T of V minus W is equal to 0, and V minus W is not equal to 0 if V is not equal to W. I'm quickly going through that because it's like it's basically the same thing. So if let V1 to Vk be a basis for the null space of T, we can extend the spaces to be a basis V1 Vk to all Vy. Be a basis for the null space of T. So basically we can choose elements in the image that are not in the kernel. If it has dimension M. And because we're able to extend it by our normal extension properties, but the thing is, since these vectors are not in the kernel, we know they're in the image. So yeah, and because these are all in the image and they span the rest, it's going to be a basis for the range. So yeah, the range of T has dimension M minus K. Let dimension of V is equal to dimension of U show that a linear map VW is injective if and only if it is surjective. This is just a property that if it's injective, the dimension of V is less than or equal to dimension of W, and if it is surjective, then dimension of V is greater than or equal to the dimension of W. Let V and W be divided into dimensional spaces. Both V is vector space of morphism. If it's a basis of V, show that T is a basis of W. Conclude that any vector space field of dimension n is isomorphic to Fn. Show that V is a basis of W. Yeah, and this will just be like simple injectivity considerations and like kernel considerations, direct sum. Not really feeling it right now. Not really vibing with this. Dual spaces. Oh man. Oh god. Okay. I want to treat this seriously, right? But like, Ah. So is there anything cool in dual spaces? Ah, gosh, okay. The thing is, I would prove a lot of this in terms of dual spaces, but the main thing is that they're covered so necessarily in something like Smooth Manifolds by John Lee, which I plan on eventually reading on stream, that I don't want to necessarily waste time with what is going to be reviewed there. So for now, I'll just leave it at that. Also because I do plan on possibly, because I'm insane, possibly finishing this book today. Or, well, today and tomorrow. I'm not going to have enough time today, considering my sessions are like usually an hour and a half. But tomorrow is definitely a possibility for, like early in the morning tomorrow, is definitely a possibility for finishing this book. So I'm just going to leave it at that, mainly so I can rest up for the next session. So I guess with that, I'll quickly also flash these on. If you don't know much linear algebra, definitely would recommend this. We would recommend this like book list. It is very good. But anyways, thank you for tuning in. Have a nice day.